Welcome to this lesson on concentration. The question of the day, what is the difference between a relative and an absolute measurement? I don't have solutions prepared for you here, but your teacher should have prepared some solutions that look something like this. One with a very faint color, one with a deep color, and one somewhere in the middle. And I would like for you to use the terms dilute and concentrated to describe each solution. The lightest of all of your solutions would probably be described as dilute. The deepest in color is concentrated, but that solution in the middle is a little bit weird. We don't exactly know what to call it. We use the terms dilute and concentrated as qualitative and relative terms to describe solutions. So had I put in a fourth solution, perhaps even lighter than this one that would, sit all the way on the left, this solution would not be able to be called dilute anymore. We would have to name the faintest solution dilute. And that is what a relative measurement really is. It's one that kind of is based on other things. And in this case, we're describing the quality of these solutions visually. So chemists have developed 4 different ways to quantitatively tell you exactly how much stuff is in your other stuff, and we call that concentration. It's based on how much solute is dissolved in a certain amount of solvent. The first way that we do this is percent by mass, and we did do a little bit of this back when we were learning stoichiometry. It is the same process, although it is a little bit different. So here we're talking about how much solute is in the solvent with respect to mass, and we're going to express that as a percent. So the solute is going to represent some mass percent of the whole thing. The solution here is the mass of the solute in grams divided by the mass of the solution in grams times 100 to turn it into a percent. You could also do this by kilograms, milligrams. It's often grams over grams, just to keep things nice and simple. We can do the same thing in percent by volume, and this is how much solute is in the solvent with respect to volume, and that's typically for when we have a liquid dissolved in another liquid. This is often, like in the real world, this is for drinking alcohol. It'll have a percent alcohol by volume, but even in rubbing alcohol, where you have like 97% or 91% alcohol, 70% alcohol, those are by volume. The equation there is the volume of the solute divided by the volume of the solution, again, multiplied by 100 to convert it into a percent. The third method is often used in environmental science and analytical chemistry, where you are going to represent it in parts per million. So again, we're talking how much solute is in the solvent. We're speaking with respect to mass, and instead of it being out of 100, we represent it out of 1,000,000. The equation here is the mass of the solute divided by the mass of the solution times 1,000,000, and our units here, instead of being percent out of 100, are going to be ppm, parts per million. A lot of the time we use this to represent amounts of like toxic or yucky things that are allowed in like tap water, for instance, or how much of a substance can be in like a natural body of water. If you do lead testing in the water, I've worked in schools that have done lead testing on the water fountains. There is a certain allowance of lead in the tap water, and that's typically measured in parts per million. And so long as we're coming underneath that acceptable level, the water is still safe to drink, and other times you're too high. It a lot of the time depends on the quality of the pipes, not necessarily the quality of the water. So that's how they judge some buildings sometimes. And then with pollutants, a lot of the time, those will also be measured in parts per million. The final way to measure molarity is in moles per liter, and I would make the argument that this is the most commonly used in chemistry courses because this is going to very easily translate into chemical reactions and to stoichiometry. And it's simply the number of moles of the solute divided by the liters of the solution. So here we have 3 moles per 1 liter. Silly joke. And that equation is represented with a capital M. It is the moles of solute divided by the liters of solution, and our units are going to be represented with a capital M, and they are red molar. So you could have a 3 molar solution if you had 3 moles per 1 liter. What's important about molarity is that they are always expressed as decimals, never, ever, ever as fractions. All of these are just solved algebraically, and it's simply a matter of finding where the numbers fit into your particular equation. For molarity, if you like to use the ratio methods for your math, which I have been teaching throughout this entire course, you would put m over 1 and then cross multiply to solve for whichever variable was missing. Again, all of these formulas are used to calculate the amount of stuff in your other stuff. So we will calculate how much solute is in the solvent or in the solution as a way to kind of get away from these terms, which aren't really all that descriptive. Scientists are looking for things that are exact, and when we have those exact numbers, we're going to have real numbers and real measurements to help describe our solutions. Please subscribe so that you don't miss the next lesson, where we will be talking about molarity specifically. Leave any questions you have in the comment section below the video, and I'll see you in the next one. Bye.